This is part 2 of our malware development series. Go ahead and watch part 1 first if you haven't already to get the most out of this video. Hey, Seb. What the hell are you doing? No! Why? Why did you do that?
I didn't know it's going to work the first time.
It did, and now all my projects are gone.
I'm sorry, man.
You know what? That's it. I had enough of your shit.
Recover files.
Did you encounter
recovering files from
like
Windows 7 through Windows 10? Everybody's been there, like rewriting a file just
Hey there, Passwiper77. I read a comment of yours on a YouTube video claiming that the Saturnians have the most advanced quantum forensics tools. Do you know a way with which I can reach out to them? Regards, Lead Cypher. Hi, Eat Cypher. Please do not email me in English, I only understand Japanese. Regards, Passwiper77. Hey there, Wiper77. I don't care if you understand English or not, just use Google Translate.
NANI?!
いろんな見た目になれるアプリなんだって。どれどれ？
Hey Zed, wake up.
NANI?!
What is it?
We're going to space.
What for?
To fix your fuck up.
Alright, let's go.
And liftoff. We have liftoff of Anne McLean to beat St. Jacques and Oleg Kononenko blasting through the Kazakh
sky. I didn't know that Saturnian jokes are that funny. Alright guys, thanks a lot for everything. Safe travels. Goodbye. Anyways, let's start this video up and talk about DLLs. But before that, I just want to mention that some of you told me that I work for the API or I'm an undercover API agent, all of that. Well,
Hey, Leet, I found your badge.
hey, what the I believe we didn't get the API's attention so far, but I'm pretty sure by the end of the series we'll be on their watch list, so watch your backs. Anyways, alright, now, first things first. Let's first talk about DLLs. DLL is an abbreviation for Dynamic Link Library. A DLL is like a special file that contains code and data that programs can use. If you happen to work on a big coding project, most of the time you'll find yourself writing a function or block of code repeatedly in your app. And since we have to follow the dry or don't repeat yourself principle in programming, we take these functions and put them in a separate file, so whenever we need them, we can just include them and that's all. DLLs work the same way. You can think of it as a collection of many programs or functions that can be shared among larger programs. Also keep in mind that a DLL is also considered a portable executable. We can confirm that by examining the DOS header in a hex editor for both an executable such as calc.exe and a DLL file like kernel32.dll. We can see that they both share the same exact DOS header, but still, if we run the file command on calc.exe and kernel32.dll, we can see that the calc.exe is identified as a GUI executable and kernel32 is identified as a DLL. But if that's the case, then how does the operating system differentiate between the two, knowing that they both share the same DOS header? Well, if we load those two files in a PE parser tool like PE Bear, we can see in the file header section the characteristics member has an additional flag set for kernel 32 DLL, which is file is a DLL. So whenever the operating system loads a portable executable, it first checks the characteristics member to determine whether this file is a DLL or a normal executable. This is just a quick explanation so that you don't get confused whenever you see a DLL file has the same header as a portable executable file. From here, we will be talking about stuff such as the Windows API and the structure of the memory space inside running processes. So I highly recommend that you first watch the previous video in which I explained these concepts in detail and then come back here. Now, to understand how DLL injection works, we first need to understand how an executable loads DLLs at runtime. When a process is run or executed, the operating system dynamically links all the necessary DLLs that the process will need at runtime. These DLLs contain the Windows APIs that the process needs for its functionality. We can use a tool such as Process Hacker to confirm that by inspecting the loaded DLLs in the memory space of our running process. Everything so far until here is legit and nothing suspicious with it. Now, if we want to abuse this behavior, we will have to first create a malicious DLL and inject it into the memory space of the target process. But we still have a problem though. You see, all of these loaded DLLs, the process uses them for its functionality. And if that's the case, how are we supposed to execute our malicious code that is inside this DLL if the target process is not using any code at all from it? Well, there are 4 DLL callbacks that we can abuse to execute code. DLL process attach, DLL process detach, DLL thread attach, and DLL thread detach. These are called callbacks, or I would rather say event listeners. If you happen to work with an awesome programming language such as JavaScript, you're probably familiar with event listeners such as onClick, onHover, onDrag, onDrop, etc. These event listeners listen for the event to occur and then execute code accordingly. For example, we can add an onClick event listener on a certain button in a web page, which when clicked, the code here is executed. The same thing goes for these 4 callbacks or event listeners. The DLL process attach event is triggered when the DLL is loaded or injected into the memory space of a certain process. The DLL process detach event is triggered when the DLL is unloaded or freed from the memory space of a certain process. The DLL thread attach event is triggered when a thread is created after the DLL is loaded. And lastly, the DLL thread detach event is triggered when a thread is terminated. We'll go through each callback in detail and how to execute it with code, just in case you didn't understand the process here. But before that, let's first create our DLL. Our quote-unquote malicious DLL here is fairly simple. In the DLL main function, which is similar to the main function in a standard C program, we check which callback was invoked. And in each of the 4 callbacks or event listeners we discussed, we call the message box Windows API, with a different message to indicate which callback was triggered. Make sure to set the compile mode to release and the architecture to x64, same as our DLL injector, which we will create next. Alright, now similar to the previous video, we will first inject this DLL into the memory space of our local process, and after that we will get nerdier and inject it into the memory space of any running process of our choosing. Sounds good? Sounds great. Alright, good. Let's do this. Alright, set. Bring out the code. Not this one, the other one. The other one. The other one. There you go. Well done. You can go now. I'll take it from here. Still can see you. Anyways, this code is fairly simple to understand. We first include the Windows header to be able to use Win API functions in our code. Again, we talked about the Windows API in detail in the previous video, so please go and watch that one first so that you can see the bigger picture here. Next, the stdio header for input and output operations. Here we have 4 Windows APIs that make this local injection happen. First, we use the load library API to load our malicious DLL into the memory space of our process from disk. If the call succeeds, it will trigger the DLL process attach callback, which executes our malicious code or the message box API in this case. Now to trigger the next callback, which is DLL thread attach, we use the create thread API. Basically, the idea here is that in order to trigger this callback, we need to create a thread that does absolutely anything. And for that, we use the create thread API and we pass to it a dummy function such as this one. If this API runs successfully, the second message box API will be executed. The last two callbacks are fairly simple. We just need to wait till the thread terminates and then we unload or free our malicious DLL. So to trigger the DLL process detach callback, we use the wait for single object API. This API halts the execution flow of the program until the specified thread returns or terminates. Once the thread terminates, the callback will be triggered and its message box API will run. Finally, we use the free library API to unload our malicious DLL and trigger the last callback. We can even comment out this API since the process will free all loaded modules or DLLs when it's about to terminate, which will trigger this callback for us. Now, before you run this program, make sure the architecture is the same as the malicious DLL, then build the solution in release mode. After the build is complete, run the program and give it the full path to the malicious DLL. We can see here our malicious DLL is loaded and the first callback is triggered. And we can even confirm that our malicious DLL is residing in the memory of our process by inspecting the loaded modules inside its memory space using Process Hacker. Moving on, we can see the rest of the callbacks are executed successfully without any issues. Just so you know, legit stuff as usual.
Next! Come on!
Alright, cool. Now, before we proceed to create our DLL injector, we need to understand the difference between two Windows APIs, load library and get module handle. Both of these APIs return a handle to a specified module or DLL. You might be asking now, if that's the case, that means I can replace this load library API with get module handle and the code will still work just fine, right? Well, no, it's not going to work. What load library does is that it loads a DLL from disk and takes care of some stuff behind the scenes, such as resolving the import address table. And once it's done, it returns a handle to the loaded DLL. Get module handle, on the other hand, just looks for the specified DLL in the list of the loaded DLLs in the process memory. If the DLL is found, it returns a pointer to the DLL base address, which is what we call a handle. So here we used load library because our malicious DLL is loaded from disk straight to the process memory. This is yet not the best way to load a malicious DLL into memory, because most of the time all of these APIs are hooked and monitored by security solutions. To get around this, we would use a technique called reflective DLL, which loads a malicious DLL straight from memory. But that's a bit advanced and I don't want to overwhelm you with any more details. So now, oh crap, I forgot to write the code. You know what? Just give me like 5 minutes and I'll be done. This is just... Alright, this is the code that makes the functionality for our DLL injector. It takes two parameters, the full path to our malicious DLL and the process ID into which this DLL will be injected. Let's assume that we will inject into MS Paint or Microsoft Paint. We can obtain its process ID by using a tool such as Process Hacker or any similar tool. Or we can do the same thing we did in a previous video, which is to take a snapshot of all running processes and search for MS Paint and retrieve its process ID if it's found. I didn't implement that here to reduce the complexity of the code and only focus on the core functionality of this DLL injector. But you can do this yourself as homework, but do not copy and paste anything. Write the whole thing from scratch and implement the process enumeration functionality and pick another process to inject into, like Notepad or something. Anyways, let's now visualize what will happen in the memory when this code is executed rather than explaining it line by line. So, imagine this is the memory map of Microsoft Paint. First things first, we get a handle to this process using the Open Process API. This API takes in three parameters: the desired access to process object, or the access rights we want to have over this process. Since we want access to all process resources, we use a process all access flag. The second parameter takes in a boolean value, and we set it to true if we want to make the child processes created by our process inherit this handle. And since we're not going to create any, we set it to false. The third parameter is the process ID which we want to access, which in our case here will be the process ID of Microsoft Paint. After this handle is obtained, we use it to allocate memory using virtual allocx. This API takes in 5 parameters: the process handle, the base address of the block of memory that we want to allocate. Since we don't know exactly where should we allocate this block of memory, we'll let the operating system do that for us by setting this parameter as null. The size of the memory that we want to allocate, and it's set to the size of the DLL path plus 1. The extra byte here is just for the terminating null byte of the string. Next parameter is the allocation type. I explained this parameter in great detail in a previous video if you want to see the full explanation. But in a nutshell, all what this parameter does is that it tells the operating system to let us write to this block of memory. Last parameter is the page permissions. Since we only want to read and write to this block of memory, we set it to page read write. After our memory is allocated, we use the write process memory API. This API takes in 5 parameters. The handle to the Microsoft Paint process, a destination to write to, a source to copy or read from, the size of the copied data, and the number of bytes read if the function succeeds. We'll just set that one to null, since it's not that important. Alright, now we have successfully written the full path of the DLL into the allocated memory inside the Microsoft Paint process. What we need to do now is to load the actual DLL into the memory space of this process. And yes, you guessed it right. We can do that by using the load library API. But the real question here, how can we force this process to execute load library for us? Well, the answer is pretty simple. We just need to obtain the virtual address of the load library API inside the memory space of the Microsoft Paint process. We first need to figure out which DLL has the load library API. From Microsoft documentation, we can see that it resides in the kernel 32 DLL. So now we get a pointer to the base address of the kernel 32 DLL using the get module handle as demonstrated before. Once we have the base address of this DLL, we need to know the exact virtual address of the load library API relative to the base address of the kernel 32 DLL. Or in plain English, we need to know how far is the load library API from the beginning of the kernel 32 DLL, since it has a ton of other APIs in it. So for that, we use the getproc address API. This API takes in 2 parameters, the base address of the DLL and what API to look for. This API will do some magic and return the virtual address of the specified API. It's not really magic, it will just access something called the export directory within the DLL and look at the export table to retrieve the address of the API. But we can call it magic for now, just for the sake of simplicity. You now might be like, wait a sec. The virtual address returned by a getproc address is the virtual address of the load library API, but only within the address space of our DLL injector process. Will this address of the load library API be the same within the address space of the Microsoft Paint process, since we will create a thread to run this API within its address space? The answer is yes. The addresses are identical in both processes. The reason for that is because the Windows operating system knows that this kernel 32 file is a DLL file, so it just loads it somewhere in memory and makes it accessible by all processes that might need it, without the need to reallocate each DLL for each running process, which in return saves much computing time and increases performance. We can confirm that a DLL such as kernel 32 is loaded in the same virtual address by checking the loaded modules for any 2 processes using the process hacker tool. So now, since we're certain that we have the right virtual address of the load library API, we just need to create a remote thread to execute this API within the Microsoft Paint process. And for that, we use the create remote thread API. This API takes in 7 parameters. We'll set all parameters to the default values except for 3. The process handle, the address of the functions to be run by the thread, and the parameter that will be passed to the function. So essentially what's actually happening here is that the thread that will be created will execute the API in this address, which in this case is the load library API, and we pass to it the allocated memory that stores the full path to our DLL as a parameter. This typecast, as demonstrated before in a previous video, converts this address to an entry point address, or in simple words, tells the created thread that this address is the start of the code that must be executed. Now the last thing we need to do is to wait for the thread to finish execution using the wait for single object API. This API takes in the handle to the thread and how long to wait for the thread to return. We set that to infinite since we want to completely halt the execution flow until the thread returns. After it returns, we close the handle to the process using close handle. After building this solution, you'll find the executable in x64 then release. I already went ahead and copied our malicious DLL in the same directory along with our DLL injector. Now, open a command prompt, make sure Microsoft Paint is running to obtain its process ID using process hacker, and then run the DLL injector and supply to it the name of DLL and the process ID. Running this, we can see the DLL callbacks were triggered. We can even force the program to trigger the DLL thread attach and deattach callbacks by using any functionality in a program that would create a thread, such as opening a file or a new window. Finally, once the program is terminated, our malicious DLL will be freed and the DLL process deattach callback is triggered. You can also find where exactly our DLL is loaded in memory by checking the modules of the Microsoft Paint process using Process Hacker. So yeah, that concludes our DLL injector. We did it, everyone. Now, as an exercise or homework for you, I want you to implement the whole thing from the ground up and add to it the process enumeration functionality so that when you run it, you supply to it the process name instead of the process ID. And if you get stuck, just watch the previous video. You'll find the code along with the executables in my GitHub, link in the description below. I also wanted to apologize for my absence for the past 6 to 7 months. This video should have been up way sooner than that. I promise there was a lot going in my life, but hopefully now things are settled. And I'm already working on the next video, which is going to be really on fire, so watch out for this one. In the previous video I told you let's get to 10k and now we're over 30, so yeah, that's really great. But you still need to subscribe though, especially when over 95% of you guys aren't, so yeah, subscribe. Really, I mean it, like you need to subscribe now, so please subscribe. If you made it this far, thank you. I really appreciate you. You're awesome. You're my hero. If this content was beneficial to you in any way and learned a thing or two from it, you can buy me a coffee and keep the show going. It's only one man with his computer. Lastly, I want to thank my Saturnian friends for restoring all my projects and files. Really don't know what would I do without you guys. Perhaps I'll start by replacing you.
Me?
Yeah, you. I'm getting a new assistant. Maybe someone with a higher IQ level than yours. Or maybe I can shoot you right here, right now, so you don't... Wait, where's my gun?
You're looking for this?
No. Wait. No.